Hi, I'm Randall Heyman, a mathematics academic. Welcome to my Corona Help playlists, now completely free of YouTube ads. If you're an educator, parent, grandparent, or student, and you'd like me to make a video on anything in primary school, secondary school, or university level mathematics, then comment me below any of my videos or drop me an email at coronahelpmathematics@gmail.com. So in the last video, we noted this beautiful theorem that links continuity to various seemingly different aspects of mathematics. We had set ourselves this task here. Actually, I wrote it here. What we want to do is use what we'd learned about open sets here to show that the sum of two continuous functions is continuous. We drew a pretty diagram. We started to write the proof. In fact, we wrote the proof. And we put in this line here. It will suffice to show that the sum of two open sets is an open set. So what we're saying is that the theorem is proven if we can just show that last little bit. So I've put here, some dashed lines, and now we're just going to try and look at this. The sum of two open sets is an open set. Okay, so let's just focus on that. I won't need what's down the bottom here. Okay, so how are we going to do this? I actually started to work through this, and I was focusing on, well, here's an open set A, oh sorry, open. Here's an open set B. And here's A plus B, which we have to show is open. What I was focusing on is taking something from here and so we put a ball around it because we know that it's open. B, we put a ball around it, and showing that when we add the two A plus B, that the ball must be within here. But it turns out there's a better way to do it, and I got this off Maths Stack Exchange, which is on the internet. A guy, Glare, wrote this. I've adapted it slightly, but I'm using his idea. It's just a slightly neater way of doing it, I think. So well done to him. So I'll use something like that, I think, in what I'm going to do. Suppose, just put my phone down now. Suppose A and B are two open sets. Let A be an element of A, of the set A. Since A is open, it's an open set, there exists I'll just use the summary, the abbreviation that we used before. There must be a ball centered on A of radius R, whatever radius we want to make it, as small as we can make it as small as we want, such that, so the ball has to be completely inside A. Okay. Okay. Then, if we take this ball and we add B, I suppose I should explain where B is for. Whoops. Okay. Now, select. So this is just an arbitrary, just like A was arbitrary in big O, an arbitrary B in B. Then, if we take the ball, the whole ball, and we add B, then we know that that must be a subset of the set A plus little b. Now, what does A plus little b equal? That actually equals, that's the set of X such that, well, what is that? That is the set X such that X is some such that X equals A plus B, where A is an element of A, any element of A. So maybe I should actually use a different letter there. So this is just a general definition of the big set A plus little b. It would be X equals C plus B, where C is an element of A. So this is a bigger set. Yeah, so I think that all works. So because this ball is within A, when we add B to both of them, well then, just like ball was a subset of A, then the ball plus B is a subset of A plus B, which equals that. Now this is in effect is a subset of this. This C can be any, this C here can be any C in A, but B is fixed. Once we set it up here, B was fixed. But now we can say that this set, big A plus little b, is just a subset of A plus B. So what does this mean? So the ball B A plus AR plus that B, which is actually equal to the ball A plus B with a radius around it of R, is wholly contained. I'll put that, is wholly contained in A plus B. Actually, maybe I should just write here what A plus B is equal to. It's the set X, where X equals C plus D, where C is an element of A and D is an element of B. Okay, so this ball is now wholly contained in A plus B, so that means that A plus B is an open set. And then now that's all we had to show. That's all we had to show to complete the whole theorem, the whole problem that we were asked to prove back up here. This thing, let me change the color. We were asked to prove that. We said we started to prove it and we proved it, except for this one line here. Still to prove. And then down here, this is this here, from here down to here, is the stuff that we still had to prove. So once we've proven that, we've proven everything. Just before I go, one little thing, and that is, we said here, suppose A and B are two open sets. But when we look at the proof, we only used A is open, an open set. We actually didn't use the fact that B is an open set. So this thing that we've proven in this video actually can be extended a little bit. You could actually say the sum of two sets, at least one of which is open, is an open set, and the proof would go in the same sort of way. So that's just something you get for free, if you like. In proving this, we've proven something that's slightly more useful. Okay, any questions on that, just comment me or email me, or if you've got any questions or any comments to make on anything in mathematics, comment or email me, and I'll try and help you if I can.